Good evening. Welcome, everybody. Before I do anything else, let me remind everybody to please turn off your cell phone. Okay? As audience member, my name is Craig Jackson. I'm an associate professor of mathematics here at Ohio Wesleyan University, and I'm a co-director of this year's Sagan National Colloquium, along with my co-director, Laurie Anderson, who's a professor in the Department of Botany and Microbiology. The National Colloquium was begun at Ohio Wesleyan in 1984 and was later endowed by OWU alumni John and Margaret Sagan. Since its inception, the National Colloquium has served as an annual forum to explore issues of national and international significance from multiple educational angles. This year's Colloquium brings together internationally recognized artists, writers, activists, and scholars from diverse fields to encourage broad conversation on current and future impacts of climate change. The timeliness and importance of this topic is hard to overstate. Climate change has the potential to profoundly impact human activity and well-being on a wide range of temporal and spatial scales, including, for example, its effect on international politics, global markets, agricultural productivity, and use of natural resources. Even the way in which we conceive of our relationship with the Earth is changing, as both individually and as a species. It's undergoing revision as we come to understand more about the ways in which human activity can affect the climate. I hope your participation in this conversation will leave you with a sense of how addressing the challenges of climate change will require collaboration and communication across disciplines, cultures, and political boundaries. Speaking of crossing boundaries, tonight's speaker is a mathematician with research interests that reach across diverse academic divisions, including biology, neuroscience, and climatology. Mary Lou Zeeman is the Wells Johnson Professor of Mathematics at Bowdoin College. She received her PhD from the University of California at Berkeley under the supervision of Mo Hirsch, and worked at the University of Texas at San Antonio for 15 years. She's held visiting positions at the Institute for Mathematics and its Application, the Mathematics Institute of Technology, otherwise known as MIT, the University of Michigan, and Cornell University. Her research interests range from the geometry of biological populations, to the pituitary glands of mice, to the dynamics of the Earth's climate system. Zeeman, however, is also engaged in substantial activity that reaches outside the ivory tower. In particular, she's involved in several initiatives focused on the health of the planet. She helped to found the Institute for Computational Sustainability based at Cornell University. She's on the organizational team of the Mathematics of Planet Earth 2013 initiative, and she's also the co-director of the Mathematics and Climate Research Network, which is an organization of leading researchers in mathematics and geosciences whose mission is to establish a new area of applied mathematics tailored to the needs of climate research. Please join me now in welcoming Mary Lou Zeeman.
Hello. Thank you, Craig, for that very kind introduction. It's lovely for me to be here. I'm impressed by this big crowd. Well done, you guys. Did you know you were coming to do math? I'm also very impressed by this series that you have developed, that your directors have developed, and the people you've had here sound wonderfully interesting. I'm jealous. I wish I could be a part of this conversation for the whole conversation. So I have to say thank you to the National Science Foundation, who fund a lot of what we do. Bowdoin, of course. This symbol is the Math of Planet Earth 2013 symbol. We're about to drop the 2013 because the Math of Planet Earth will continue as long as we have a planet, we hope. And this is the Math Climate Research Network, of which Craig is a member. So if you want to learn more about that, talk to Craig. So if there's one message to take away today, to add to the messages you're getting. It's Google this site. Google Math of Planet Earth 2013. There's a huge amount of activity and a lot of stuff you can learn from up there. So this, these events, there are all kinds of events like this one all over the place. Lots of them are streamed, so you can watch them later. There's a daily blog, which has really got interesting information on it. And there's an education page with lots of stuff that, if you're a student, you might just enjoy. If you're a professor, the stuff you can bring into your classroom. So here's our path today. I want to talk about math and sustainability for a little bit, and then define or help understand, I think I'm a bit close to that. Help understand how mathematicians think about tipping points. Because we hear a lot about them, we worry about them, and yet they're actually mathematically not so difficult to think about. We have good ways of modeling them, which can help us maybe think about ways of predicting them or avoiding them, or using them, depending what we want. So I think it's a really useful topic to learn about. And to do that, we have to go through, we will go through alternative stable states, and then we'll think about resilience. We'll change our environment, and finally see how that might fit in with decision support questions. So first of all, what are some components of sustainability? I hope this touches most people in the room. All these different things, natural resources, energy, economics, public policy, the environment, education, us, humans, climate, they're all parts of sustainability. I borrowed this slide from Peter March when he made it when he was head of mathematical sciences at the National Science Foundation. So, of course, the next one is, look at the role the mathematical sciences can play. They can bring cohesion to sustainability because you need a language to pull all these subjects together. Mathematics can be that language. And I showed this slide recently, and at the end of the talk, somebody came up to me and said, no, it's geography in there. Geography is the language that pulls all these together. And you know, when you think about it, it's so interdisciplinary, anything can pull them together. I think really important is that literature can pull them together. You had a writer here come and give one of these talks recently. I don't know if you guys have read this. This is a recent novel by Barbara Kingsolver. She's an incredibly popular novelist. And this is all about how we perceive climate change. And she's trying to help us understand how different people communicate to each other about climate change through a beautiful novel. But let's go back to the role that math can play, or any of us. You guys, you're the generation that's facing this, really. You're facing this global change, and to understand it and make good decisions about it, you need to be incredibly interdisciplinary, more interdisciplinary than your teachers have been, typically. And it takes a huge amount of courage. So I'm here to recognize that you guys are courageous, and you need to be courageous, and we really should value that. And courage, what is courage? Courage is going ahead even though you're frightened. Courage doesn't mean you're not frightened. It's okay to be frightened to have to study all that stuff at once. Courage means going ahead and doing it anyway. And we need courage, all of us teachers need courage to help you do that, even though we weren't trained to do it. So we're all learning together. And this is a possible outcome, right? I like this. So all this discussion about climate, it doesn't really matter whether you believe that there is global change or not, if these are the things that you're working towards. And typically that's what we're working towards as we think about global change. And I think it's very important that as we think about it and as we educate about it, we're educating through hope, not fear. And that the conversation you're bringing up here is a conversation of hope, not a conversation of fear. Okay, so let's think about climate a bit. You may well have seen these pictures 10 times already, but I just want to show you some of the classic observations. Back in September of this year, the 5th assessment report of the Intergovernmental Panel on Climate Change was released. That panel is a panel of scientists, climate scientists volunteering to survey the literature, to write a report, governments around the world can use to understand the state of climate science and the state of climate change. And this is a very famous sentence from that report. Warming of the climate system is unequivocal. And since the 1950s, many of the observed changes are unprecedented over decades to millennia. And so I'm going to show you just a few of their graphs of the observations. So this is the increasing CO2 in the atmosphere. The red one is from Hawaii, the black one is from the South Pole. The oscillations represent the seasons, and they're different amplitudes because there's more greenery in the northern hemisphere than the southern hemisphere. This one is about globally averaged temperature since 1850. The top one is annually averaged. The bottom one is averaged by decade, so that you can see whether you're thinking, you can sort of ignore the little fluctuations when you look more carefully, when you look at the decades and see the change, see the pattern. This one is about Arctic summer sea ice. So this is measuring the total area of sea ice in the Arctic over in summer, and that's declining. This one is, I said we're supposed to do it by hope, and here I am showing you all the change, and the change we tend to find rather disturbing and frightening. Sea level rise, observation is clearly rising, and the last observation I'll show you is about ocean acidification. So this is the surface ocean, that's the concentration of carbon dioxide in the ocean, and of course it's increasing because it's increasing in the atmosphere, and the atmosphere and the ocean balance, equilibrate. And because of that increased CO2 in the ocean, the pH is decreasing, which lower pH means more acid. So those are observations. They're not really under any question. The human influence on the climate system is clear. Here's a role that math can play. Climate prediction is still difficult. Why is that? Why is it that we can make these observations, it's crystal clear what's going on, but we're still not very good at predicting what will happen in the future? And some of the mathematical reasons underlying the difficulty in prediction are these. The climate system is complex. It has mathematical chaos in it. We all know that it's very difficult to predict the weather, and that's about the intrinsic chaotic nature of the weather, which means that you know about the butterfly effect, the sensitive dependence on initial condition. If a butterfly flaps its wings in Australia, then it's going to change the weather in Ohio, that kind of idea. That's chaos. There is uncertainty in the sense that we don't even know whether we're measuring accurately or not. How do you measure what the temperature and the weather is in the middle of the ocean? What do you put there to measure it? And how do you cover the whole ocean with your measurements? And then there are these tipping points. The system can tip. So we're going to focus on this one. All these have interesting mathematics behind them that are fun to think about, but we'll focus on tipping. And you could ask the question, why do we want to predict the future? It's maybe we'd rather just see what happens. Predicting the future, having a model that can predict the future is really useful for helping the people who've got to make decisions about how we spend our money. What are we actually going to do to try and reduce climate change, to try and reduce our biodiversity loss, try to maintain biodiversity, try to maintain our food systems, try to maintain our water supply, do all that hopeful stuff? Well, how do we actually spend our money to do all that hopeful stuff? That requires making decisions about how to spend the money. That requires policy and management. And we, academics, have a lot to offer to people making those policy and management decisions. They don't have the time to do all the science. So predicting the future gives us a way of scenario testing for the people who are trying to make a decision between different scenarios. And this presents lots of mathematical challenges and lots of mathematical opportunities. And so I'm a firm believer that whatever your talent and whatever your passion, you can use them to help the planet. If your talent and passion happen to be that you love math, go for it, do math and use it to help the planet. If it happens to be that you love writing novels, do that. If it happens to be that you love being out in the wilderness, do that. Whatever you love, you can focus on helping the planet if you want. Today we're going to pretend that we all love math. And we don't even have to pretend, right? It's true. But all these mathematical features also show up all over here, all around this circle, all across sustainability challenges. So let's think about alternative stable states. I'm going to talk about simple dynamical systems that we can all get insight from. Prediction often involves really big, complex computational models. One of the challenges is how do we go in between here? So for those of you who are mathematical or physical or computational or scientific, you can be thinking, yeah, what does go in between? What level do I like thinking about? And you can be thinking at the level you want to think. So we'll talk about a very basic climate model. Here's, we're going to be talking about the Earth's energy balance. So here's, have you guys seen this recently? I'm getting nods and shaking of heads, okay. So this is a cartoon of the energy coming in to the Earth and leaving the Earth. So here, this is energy coming in from the sun. And some of the energy just gets sent off by clouds. But a lot of it comes to the Earth. The Earth absorbs some of it, but the Earth also reflects some of it. That reflection is called albedo. The process of heating up the Earth, the process of absorbing energy heats up the Earth, and then the Earth radiates energy back out again at a different wavelength. The sun is really hot, so it radiates at a very high wavelength, very short wavelength. And the Earth is only warm, so it radiates at a long wavelength. But the Earth radiates energy out again. Some of that energy makes it all the way through the atmosphere and escapes. But some of that energy gets trapped by the greenhouse gases that we hear so much about and has an effect of warming the Earth back up again. If you want to learn more about that, these are some really good books about it, and I can leave these slides here for you. There's one that's just come out by Hans Kapper and Hans Engler about math and climate, and then you also have a source right here. Craig is a great resource for learning about math and climate. So we're not going to deal with that whole picture of all the energy coming in and out. We're just going to think of the Earth as this round blob. And there's energy coming into the Earth from the sun, and there's energy leaving the Earth through that warm radiation. And that energy depends, in particular, on albedo. So we're going to think about how the reflectivity of the Earth and the greenhouse gases interact. Those are the two climate processes we'll think about. So the Earth reflects energy, and greenhouse gases trap it. So albedo, that reflectivity, is really high if you're shiny and white. A lot of stuff gets reflected. So it's measuring the amount of reflection. It's bigger than 0.8 for ice and snow. If everything was reflected, that would be an albedo of 1. Right? If nothing is reflected, that's an albedo of 0. Dark blue ocean absorbs almost everything, only reflects a little bit, so it's an albedo of 0.2. So let's think about some extremes. What happens if the temperature of the Earth is really low? And I don't mean like it's just winter. I mean it's negative 50 all over the planet. What would the planet be like? It would be covered in snow and ice. It would be white and shiny all over. It would reflect almost all the sunlight coming in. And so the albedo would be, the energy in would be really low. So when I say temperature is very low, I mean really low, and the energy in is really low. Snowball Earth, that's called. At the other extreme, the temperature could be really high, way higher than it is now. So there's no snow or ice anywhere, an ice-free Earth, and then the energy in would be really high because we'd absorb a lot of it. So we can draw a graph of that. That's the simplest graph that captures that. Here's the global average temperature of the Earth. When the temperature is really low, the energy coming in is really low because most of it's reflected, like a snowball. And when the temperature is really high, the energy coming in will be really high. And let's just do the simplest thing we can and connect them smoothly. So where it connects, that's like having an ice cap gradually growing and covering the whole planet. Okay, so that's a straightforward graph to understand. Now what about the energy out? Here we'll use classical physics. We treat the Earth as a black body, which that black body idea just says whatever temperature you are, you radiate a certain amount of energy, and the amount of energy you radiate is modeled by this formula, sigma T to the 4, T is temperature. So T to the 4 it's like T squared, only steeper. So you radiate that much, and sigma is some constant. It's called the Stefan-Boltzmann constant. And so what's this little epsilon thing here? That's capturing our greenhouse gases. So the Earth is radiating sigma T to the 4, but it doesn't all get out. It doesn't all escape past the atmosphere. So when epsilon is 0, what does that mean? Epsilon is 0. So we've got a 0 in front of here. So how much energy is going out? Nothing. As epsilon 0 means the greenhouse gases are trapping everything. It means lots of greenhouse gas. Epsilon equal 1 says everything's leaving, nothing's trapped, no greenhouse gas. So greenhouse gas and epsilon kind of work backwards with respect to each other. But here's a graph of sigma T to the 4. Sigma's just some constant, epsilon's just some constant. So it's a graph of, epsilon sigma T to the 4. It has that almost quadratic looking shape. Now let's put those two graphs together. And I've put them together so that they overlap each other like that and intersect. The underlying assumption of an energy balance model is that the Earth's global average temperature is driven by the energy imbalance. So it's driven by the energy in minus the energy out. If there's more energy coming in than leaving, the Earth will heat up. The temperature will increase. The rate of change of temperature will be positive. This symbol, the T by dt, wonderful choice of notation. The derivative of temperature with respect to time just means the rate of change of temperature. So is the temperature going up or is it going down? If there's more energy coming in than out, the temperature will go up. The Earth will warm. If there's more energy leaving, the temperature will cool. The temperature will go down. So that's the basic assumption underlying an energy balance model. And that energy balance underlies all the big complex climate models as well. There's a lot more to them, but that's at the core. So what happens at that point? What's going to happen to the temperature if you're at that point? So the energy out and the energy in are the same, which means this is 0. What's happening to the temperature? It's going to stay constant. You're in equilibrium. So the rate of change of temperature is 0. It's in equilibrium. Where else do we have equilibrium? At B and C, we also have equilibrium. And what is that equilibrium? Where is that equilibrium? What's that planet like? We just said if the temperature is here, we'll be at equilibrium, the temperature won't change. What's that planet like? It's really cold, remember? That's low temperature, low energy. It's covered in snow. Earth. Ooh, I'm back. Okay. What happens if your temperature is in between B and C? Would the Earth stay at that temperature? Would it increase temperature? Would it decrease temperature? Right, you guys are saying the right thing. The energy in is higher than the energy out. So this would be positive, so the temperature would increase. And out here, the temperature would decrease. So look at that. There's something special about this point. The temperature just wants to go there. And you can do the same around here, and you'll get those arrows. And now you have a lot of information about how does the temperature of the Earth evolve, just drawn on that axis. So let's extract that axis. There's a whole bunch of information that's useful to us. And now I'm going to take that axis and stand it up. For reasons that you will see later, but for now, we're just going to stand it up. We're going to stand it up. There it is. So this point at the top is that one. It's the Earth with either no ice or ice caps. This point at the bottom that attracts is the snowball Earth. And here we have two different stable states. Remember what we were trying to develop was multiple stable states. This system could be stable. There's feedback which can drive that system to being a warm Earth. If we start up here, there's not enough ice to cool it down, and instead there's enough heat to warm it up. So the feedback drives the system to this stable point. But if we start with the temperature down here, there's already enough ice and snow on the Earth that this feedback drives it to this totally snowball state. So you think of these feedbacks driving in opposite directions. So that's one example of an alternative stable state. Let's look at a few more, because now, once you get that in your mind, you see it everywhere. Oh, let's not. Let's ask this question first. We just said these are both stable states. We said this is a stable state. 600 million years ago, there is evidence in the geological record that the Earth was in this state. So that begs the question, if that state is stable, how did we ever escape from it? Why is the Earth not still in that state? So we'll come back to that. But it's something to ponder. Okay, now let's look at some other examples. We're going to switch to ecology. This is a classic example in ecology of alternative stable states. A shallow lake. How does a shallow lake work? It's shallow. It means the sunlight can penetrate through the water and reach the bottom of the lake. And the sunlight can reach through, and so vegetation can grow, and because there's vegetation, there's lots of biodiversity, and it supports fish, it supports the things that eat the fish. So there's all this beautiful biodiversity in a nice clear lake. An alternative is the lake gets turbid. Turbid means it's just not very transparent, and there's stuff in the water making it look green or brown. It's either algae or it's sediment from the bottom of the lake or whatever it is. And when you get into that state, then the vegetation can't grow, so there's nothing to anchor the sediment, and so all the waves and the wind can keep the sediment churning, and the fish keep the sediment churning, and because it's dark, it stays dark. You see there's a feedback there. And it's been observed that lakes tend to occur in these two extremes. So this is a graph of vegetation cover, and this is a graph of number of lakes found like that. So here are lakes with almost no vegetation because they're turbid, and here are lakes with lots of vegetation, they're clear. And you see that there are lakes in between, but most of them are one extreme or the other. And moreover, there's lots of evidence that lakes switch between the two states quite fast. So in the real world, sudden dramatic change can and does happen, sudden dramatic flip from one stable state to another. Here's another example. In the Florida Everglades, they used to be dominated by sawgrass, but every time a patch of sawgrass gets cleared for some reason, then cattails take over. That didn't used to happen, but now it does. So gradually the Everglades are converting from sawgrass to cattails. So, and again, this is another example of alternative stable states. Coral reef, we hear a lot about that. Corals can be coral dominated with high biodiversity, or they can be algal dominated. And again, we see them switch from one stage to another. Disease, we know how disease spreads through a population. So there's sudden dramatic change from the disease-free state to an endemic state or epidemic state. Fisheries, we're used to the idea, or maybe you're not, I don't know if you've discussed this, that if we harvest a fishery, we harvest and harvest and harvest, and we gradually increase the harvest, and suddenly the fishery might collapse. Not always, but in many examples. Here's one that might be closer to home if you guys have been out in a boat. If you ever go kayaking, you know there's the stable state, which is, there's the preferred stable state when you're upright, and there's the less preferred wet stable state. Unless you're a little kid. Little kids like this state. Going into neuroscience or behavior, we're also familiar with this, the stress axis. Do we fight or do we flee? They tend to be two sides of the same coin, right? Alternative stable states. Mood, we know this too, that we tend to flip between our moods rather extremely. We probably all know people who struggle with eating disorders, where we're flipping between two extremes again. So the point I was making is that these alternative stable states are all over science. And While I'm talking, the math I'm talking about is simple at this level. Those things I was talking about were in the real world, and so we would like to be able to take those ideas through, these ideas of sudden dramatic change can and do happen. We'd like to take that through to the complex models as well. So now let's think about resilience. So if you are a manager, if you're trying to figure out management policy or carbon tax policy or whatever kind of policy you're thinking about, the kind of questions that come up if you think you've got alternative stable states is, are we at risk of a regime shift? Are we going to shift from one regime to the other? Is our state resilient enough? Whatever resilience means. At least in English, we know what we mean by that. How do we avoid a regime shift? How do we maintain enough resilience? Or maybe we want to force a regime shift. How do we reduce the resilience so that we can force regime shift? Those are kinds of questions that come up. These are I like to show these, especially for that last example. So here's another example of alternative stable states that you might know these little toys. It's a little plastic rubbery disc, and it can be stable that way up or this way up. Do you know what's going to happen? Yeah, when it changed its state, it wasn't really quite stable in that other configuration. And when it changed suddenly, and that sudden change pushed against the table, right? And so we were waiting to see if it changed. It was really frightening, wondering if we were going to reach that tipping point. So here's my favorite toy. Same idea, same little rubber thing, only we can take control. So I'm just going to take control. I'm going to make this tip when I want it to tip. Right? So I like this because it shows you a tipping point doesn't have to be a frightening thing. Sometimes it's something you really want to take control of to make something good happen. Okay, resilience. So when we ask what is resilience, we need to ask more. Resilience of what to what? Resilience of some stable state to some perturbation. How much perturbation can the system withstand and maintain its function? So suppose the system is at state C, our state C. What happens if you perturb it to here? What's going to happen? It's going to go back up to C. It will recover. What happens if you perturb it down there? Feedback's going to push it down to B. It does not recover. You get a regime shift to a different state. Think about the lake. It was clear and vegetated. What happens if too much algae grow? The feedback pushes it down to this turbid state. How much do you have to fix it? Do you have to change it all the way up to here? How much do you have to perturb the lake to fix it? You only have to, if it's already turbid, you only have to perturb it up to there. Because after you perturb it up to there, which you could do maybe by removing some of those fish that are churning up the bottom, once you get it up to there, it's going to recover on its own. That's a really nice thing to understand if you're the one who's got to pay for fixing it. So resilience is about this, what we call the basin of attraction of the stable state. And one of the challenges for us, one of the things I think that mathematicians and scientists could really do that's fun, would be to figure out how to quantify resilience in different situations. So we have to ask the question, what's the distribution of perturbations or shocks or noise or whatever you're going to call it? What's the distribution of those shocks that your system really gets? Are you thinking about agriculture? How much rain does it get? How frequently does it rain? With climate change, that's going to change. Are you thinking about a forest? How often is there a fire? And so on. And then the other part of the question is, how does that noise accumulation, you've got all these shocks happening, how does that interact with the dynamics that are attracting to your stable state? Who wins, the dynamics or the perturbations? So is the basin large enough to contain your accumulated shocks? I think that's a really interesting question. And that question can be asked all the way through these series of models. And this question, the noise characteristics and accumulation behavior asked all the way through the series of models. So now let's take all those ideas and put them into our gradually changing environment. Oh, and so when we do that, I want to channel my father a little bit. So my father is Sir Christopher Zeeman. He's a mathematician, and in 1978 he gave the Christmas lectures, which are televised lectures in England. They're on TV the week before, between Christmas and New Year. They're about science, and they're designed to keep kids off the street. Wouldn't that keep you off the street, science lectures on TV? It was the 150th time, well, 149th time that the Christmas lectures were given, and it was the first time they were about math. And he called them mathematics into pictures. So this is not me, but it could be me. It shows you what my childhood was like. He just loves math and he loves kids. And there are 6 lectures, and the last one is on catastrophe theory, which is tipping points. So he divided the world. This is how he thought about the world. This is the way I grew up thinking about the world, and I think is a really useful framework to share. He divided the things into discrete and continuous, and he divided behavior into discrete and continuous. So here's the first box, discrete things behaving discretely, like when you throw a dice, it's going to land on one face. And the kind of math we have developed for that is finite probability of finite groups. The next box is this one down here, discrete things behaving continuously, like the planets, the Earth moving around the sun, yes, that way around. So what makes it continuous is time, so we call that the time box. Next box is about continuous things behaving continuously. That's really not very surprising that they should do that, and so, for example, waves, the math we've developed for that is partial differential equations. But here's the box full of surprises. When you have continuous things that jump, continuous things that behave discretely, that's tipping. We have all this language for it. Tipping points is the modern language. Critical thresholds is a more ecological language. Phase transitions is the physics language. The math we've developed is bifurcation theory and catastrophe theory. And my father called that Pandora's box. So we'll go into Pandora's box now. And for the mathematicians, what I'm going to do is describe a tipping point as a saddle node bifurcation. It's not the only way something could tip, but it's really good intuition to have. So let's go back to our climate example. And let's increase epsilon. So remember, epsilon was the parameter that was measuring how much greenhouse gas we have. And epsilon went backwards from greenhouse gases. If we increase epsilon, that means that we're allowing more stuff to escape, right? And so increasing epsilon is like lowering the greenhouse gases, which we're not very good at, but that's what we're going to imagine doing. So what's going to happen to the graph? When we increase epsilon, what's going to happen to this graph that's got epsilon in it? Yeah. People are pointing that it's going to go up. It's going to get scaled up a little bit. There it is, it's gone up. What's happened to our stable points? To our different stable states? This one moved a little bit. These two moved together. Let's increase epsilon some more. Whoa, those two have coalesced. What's going to happen when we increase epsilon even more? They're gone. They're just gone all of a sudden. And the fact that they're gone means there's no equilibrium up here. There's nowhere for the energy to balance up there anymore. The only place the energy can balance is down here at Snowball. But it's okay, we're not very good at lowering the greenhouse gases. We're not worried about that happening. Let's do the opposite. Let's decrease epsilon. Let's increase the greenhouse gases. We're very good at this experiment. So increase the greenhouse gases. What happens to our equilibria? This one moves up a little bit, and these two move together. And as we increase the greenhouse gases some more, then those two disappear, and the only place the Earth's energy can balance is at some high temperature, which might be with ice caps like now, or it might be without ice, but it's definitely not a Snowball temperature. So this picture is why we put the phase line vertical. Here we are stacking up all those phase lines together. right? Do you recognize them all? This is the one we just looked at where the only stable state is high temperature. This is the one where the only stable state was low temperature, so that was low epsilon, and this is that's low greenhouse gas, and that's high greenhouse gas. And so if we did that for every single value in here, we would build that cute curve. So down here is the low greenhouse gas concentration, and the only equilibrium is snowball Earth. Here's the high greenhouse gas concentration, the only equilibrium is that hot Earth. And the models suggest, and our observations suggest, that we're in this situation at the moment, that we could be stable up here, and we are stable up here with some ice caps, but we could also be stable down here at snowball Earth, given the amount of energy that comes from the sun and the amount of greenhouse gas that we have. But we're at this stable state. So let's return to that question. We used to be at this stable state. How did we ever get out of it? Do you guys know? So imagine the story. We were down at snowball Earth. The whole planet was covered with snow and ice. It's 600 million years ago. There's precious little life on Earth. So there's not much carbon being drawn out of the atmosphere through any kind of life, any kind of respiration. There's no carbon being drawn out of the atmosphere through the weathering of rocks because they're all covered in ice and snow. So carbon is not being drawn out of the atmosphere. But carbon is being put into the atmosphere. Do you know how? Can you imagine how? What can still work even though you're covered with snow and ice? The interior of the Earth is still warm. We still have volcanoes. So the volcanoes are still putting carbon dioxide into the atmosphere. And gradually, over many, many thousands, hundreds of thousands of years, I don't know how many, the carbon content of the atmosphere increases to much higher, orders of magnitude higher than it is now. And that allows us to escape. So let's see that on our graphs. Watch what happens to the basin of attraction of that stable state on the graphs. So we were down here, the snowball state, but because of the volcanoes, we're going to gradually increase the greenhouse gas concentration. We're going to move along this axis. So we've suddenly gone from having only the system on one line to having a two-dimensional system that's got a slowly varying parameter, a slow time scale that's changing things, a gradually changing environment. Does that sound familiar? So we gradually increase, the volcanoes gradually increase the greenhouse gas, and so we were at this state, but we slightly increase to that stable state. And when we increase the greenhouse gases some more, we increase our stable state slightly. And as we keep increasing the greenhouse gases, the resilience of this stable state is really getting small, thin, sad for the stable state, till we get beyond the point where the energy can balance here. The energy can no longer balance down here, and it jumps up on a much faster time scale than this. It jumps up to the high energy equilibrium. And so now, the high temperature equilibrium means things can melt, right? So all that snow can melt, and the rocks are exposed. And now that the rocks are exposed, you can start drawing carbon out of the atmosphere. And so as you draw carbon out of the atmosphere, you're going to move back down this equilibrium, back down this axis. And so you can balance back where we are in this state. And one thing to notice, this is something that we associate with tipping points a lot, is we tipped from the snowball state, we tipped up to the current state. To tip back, you have to do a lot. It's not enough to just go back here. Because we're now up at this state, if we reduce greenhouse gases, we're up here and we're going to keep following that stable state until we're forced to jump down again. So undoing what we did takes a lot more work than doing it. That's one of the qualities of a tipping point, is that it's difficult to undo. It's not impossible, but difficult. So I should just point out, here's a picture of our paleoclimate history. So we were talking, the snowball Earth state was 600 million years ago. This graph goes down to 70 million years ago. This is the present, this is 70 million years ago. And this is a proxy telling us our temperature. So our temperature's been varying, Our temperature's been varying. This is low temperature, this is higher temperature, lower temperature, higher temperature. And so just squished in here is our recent ice ages. So here's 500 million years ago, where in interglacial, and then the temperature gradually decreases to an ice age, and then we suddenly warm up to this kind of temperature, and then we gradually decrease to an ice age, and then suddenly warm up again. And here we are, suddenly warmed up to our current temperatures. So you can see qualities of tipping there as well, right? But the model that I've just described to you contains none of that detail, none of that sophistication. All that stuff is in here. You need to develop more models with more climate processes in them to be able to capture those interesting features of the climate record. But as we said, there are lots of interesting features in there. If you would like to learn more about it, go to this education page. On this education page, there's a link to a short course about climate models. Craig knows all about that short course. He can tell you all about this stuff. And there's a route to moving forward with this math. Let's now look at our shallow lake. Think about the turbidity of that. What happens with those lakes is it's to do with the way we treat the land around them. When we farm, if we're putting on fertilizer and there are more nutrients being drained into the lake, and those nutrients are feeding the algae, and the algae grow, and you get more turbid. So I've had to draw these backwards to make it match the picture. Here's low nutrient loading, and the lake is clear. But as you gradually increase the nutrient loading, the lake is clear, it's clear, it's clear, it's clear, until suddenly it jumps to being turbid. And then you have to do more. You have to either pull the nutrient loading all the way back here to allow it to jump up, or you pull the nutrient loading back a bit and then do that fish removal thing just to get above this threshold. And then it can build itself back up. And that same nutrient loading explains the Everglades story with the sawgrass and the cattails, and the coral story. It's the agricultural runoff into the water systems around the world. Or the toy disc is it's slowly changing environment. Its elasticity is slowly changing its environment, and so it jumps from concave down to concave up and off the table. So now let's finish by thinking about decision support a bit. So we've talked about resilience as the ability to withstand perturbation. And this can be useful. Let's think about what's difficult about it. What's difficult about tipping points is you don't get much warning, right? This value didn't change much before it jumped. So how do you know when you're going to jump? As you're just trundling along happily at this value, and then suddenly you jump. Or you're trundling along quite high and suddenly you jump massively down. So the value of the stable state is not giving you enough warning about the tipping. So how can we get some warning about the tipping? So let's think about the next level of math. This resilience issue can really help us. This basin of attraction, let's think about it. Here, that was an equilibrium. Things didn't change there at that point. And up here, they don't change. But in between, they have time to change a lot. They change a lot. But as you get close to this tipping point, those two equilibria get really close together. The zero derivatives get really close together. So things don't change very fast in between there. So the rate of change is slowing down. It's called critical slowing down. As you get close to this bifurcation, this tipping point, you get critical slowing down. Let's exploit that structure. Let's see what we can do with it. So I borrowed this slide from Martin Scheffer. He is in Europe, and he is leading the charge on thinking about how we might be able to find early warning signals for tipping. So he says, can critical transitions be predicted even if we don't understand the system? That's a tall order. And what he's doing is saying, we spotted a pattern down here. When we look at those low-dimensional systems, when we look at that picture I just showed you, and we think about this critical slowing down, we found a pattern here. Let's test it. Let's test it with the big real-world data and see if the pattern's there. So let's look more carefully at the pattern. So the pattern is that things slow down slowly. Perturbations slow down slowly. And nature is full of perturbations. Nature gives us noise all the time. Instead of saying, oh, that's noisy, that's difficult, let's say, it's noisy, it's useful. Let's use that noise as perturbation. So here I've drawn a graph of something that's traveling along the red and jumping up, right? Now let's put noise on top of it. So here's a noisy thing, basically traveling along that stable state, but suddenly jumping up. Look at the qualities of the noise. Down here, where we're not close to this state, where things can return to equilibrium very fast, the noise does return to equilibrium very fast. It's just all bouncing around equilibrium. Up here, the noise does not return very fast. It returns slowly. And that slowing down of perturbations increases the system's memory. And the increased memory means you get increased autocorrelation. That means the noise stays on one side of the curve. It stays in one area for a while and then flips and stays in another area for a while. But it hangs around. That's autocorrelation. Increased variance. It manages to escape further from its stable state in either direction. So all those things happen just because the stable state is lowering its resilience. So this Martin Scheffer is looking for that signal in all kinds of real data. So he's looked at all kinds of data from the paleoclimate record. Here are 8 examples. Dakos and Scheffer and others have looked at these 8 examples. And they say that in every case, if they look at the autocorrelation signature, so here's the climate data, the detail of the climate data, and underneath is the autocorrelation signature. Remember, the autocorrelation is kind of measuring the system's memory. That just before the jump, there was a signature. It doesn't mean that every time there's a signature, there's a jump. They're not claiming that. What they're claiming is that before the jump, there was a signature. So we should maybe learn more about these signatures and pay attention to them. So again, what they're doing is saying they spotted a pattern down here. Let's test it in the real data. They find it in the lakes. They find it in financial markets. It's well known in the power grid for power cascades. And people are now thinking about it in psychology. So that is not enough for us to base our policy on it. But it is enough, I think, for us to say, whoa, that is really interesting. It's really interesting that that pattern shows up. We need to understand how that pattern shows up here. There is room to do a lot of science and a lot of math, thinking about why that works, sometimes, ever, in the bigger systems. So it's inspiring. It's not only me who thinks it's interesting. A lot of people think it's interesting. So it's inspiring a lot of research questions. And a lot of people saying, your method's not good enough. My method's better. Well, that's OK. That's how research works, and we get a lot of science done. So let's finish off by thinking about situations where we can control, where we have some control. The previous situation was where we didn't really have control. We were watching this changing environment, and can we predict that it's going to tip? It would be useful for us to know that it's going to tip. Now let's switch to situations where maybe we do have some control over the environment. We can make the change. So these would be like our land use, our water allocation, how we treat our natural resources, how we plan, and things like that. So our goal then could be to manage for resilience. If we want to keep things healthy, we might want to manage them to maintain high resilience. So I would like to channel my father once more and think about what if a decision maker, instead of just having one degree of control, so at the moment, managing resilience means let's run away from the tip, right? Let's keep away from the tipping point that we've only got one axis on which to play. Suppose you've got more than one axis on which to play. Maybe you've got a few degrees of control, a few different ways you could spend your money. Like you could reduce the nutrient loading, or you could take out the fish. That's 2 different ways you could spend money to try and fix the lake. So this is my father again with his catastrophe machine. And he did a lot of work thinking about situations where you have more than one dimension of control. So here's a generic picture. If your system has a minimizing principle, like minimizing energy, here's a generic picture for the equilibrium surface now. Before we were looking at the stable states, this was our curve, right? You recognize that red and blue curve at the front. But if you have another dimension of control, it's highly likely that you get this full 2-dimensional picture which has a fold in the front but does not have a fold in the back. So think about what that means. If you're in the front, you've got these tipping points, it's hard to reverse them, you don't get much warning for what's happening. If you're at the back, you have this smooth increase. You get lots of warning about what's going on. You can see it in your level, and you can undo it. You don't have that same tipping point stress. This factor is, he calls the normal factor. This factor that splits apart your stable states is called the splitting factor. And some things that control the splitting factor are the strength of feedback in your system. Maybe you have some control over that. The network connectivity of your system. Again, something you might be able to control. Woo! The network the depth of the lake. I don't know how you control that. Level of homogenization in a model. In just a last word, in these climate models, if an example, I've seen talks where people are thinking about the forest, so they're putting forests into the climate model, and they might model the forest as having one kind of tree with one kind of leaf, one kind of average leaf. And when they do that, they find, sorry, I keep doing that. They find terrible tips in the forest. But when they put in a more heterogeneous forest with different kinds of trees, with different kinds of leaves and different kind of response to the environment, they find a more smooth tip. Or not a tip, a more smooth transition. So it's important for us in thinking about how we're modeling, and that last thing that you keep seeing and I keep taking away is that it could offer us more policy insights. If we were even aware that there's a chance that we could just take away this tipping phenomenon from the particular management decision. If you're interested in that, go Google him. Google Sir Christopher Zeeman and watch the 6th Christmas lecture. There are 6 lectures about math. They're beautiful. You could watch them all. Thank you.
I'd ask you to raise your hand and I'll come around and hold the mic for you.
Slides, the book slide, okay. There's an awful lot of slides. I'll just scroll. And are there any other questions? Go ahead. Oh, sorry. Craig is doing this. I'll scroll.
So during the slide that you... Yeah. So you say that we are at the middle of the graph, and we at the low point or the up point?
The upper part.
Up point, so...
Right.
I just wonder, like, if you want to go to the down point, you have to go past the blue lines. But the only way to go past the blue line is like to decrease the temperature.
Oh yeah, you're right. You're right. I keep saying we have to do it this way, but another way is to force ourselves down below the threshold.
Yeah, but like to go down there, you have to decrease the temperature, right?
This would well, yes. How would you get down there? Because in the Earth system example, this was the energy that we receive. So to go down there, you'd be saying, I want to force myself to receive less energy. So I guess this is the kind of thing people are doing when they talk about geoengineering. And let's just put great big umbrellas up there. Right? If you put a great big umbrella in the sky, then we receive less energy. And that would be a way of forcing yourself down here a little bit.
Oh, so you control energy by something else rather than temperature.
Right, right.
Okay.
Of course, there are reasons that would be a crazy idea. It wouldn't really help with the ocean acidification problem, I'll just mention. But, oh, I'm flipping backwards, right? Back.
Okay, I'll get you a second.
When you say, do I hold it? Okay, right. When you say sudden change...
Where are you?
I'm over here.
Oh, thank you.
Yeah. When you say sudden change, like how sudden is...
Yes, that's a really good question. How sudden is sudden? So that's, the way I've described this, it was all about a timescale issue. It was all about this, so the dynamic that's going on here, the kind of dynamic here, whatever timescale that's on is quite fast. And you know, if it's glaciers, it's actually glacial, but we're thinking of that as fast, compared to the whatever it is that's moving the slowly changing environment. So I mean sudden relative to the changing environment. So it's, in math, you think about fast, slow timescale separation. You're changing one thing slowly, but the result, when you jump, happens on the timescale of the dynamics in this picture. So the result happens in the fast dynamic. So it's all relative suddenness. Does that answer what you were? Yeah, good.
Yeah.
Tell me when I get there. Go ahead.
Okay. So is there talk of mitigating incoming albedo that's maybe less crazy than putting up giant umbrellas?
There's certainly lots of, there's lots of discussion of geoengineering ideas, and I am not an expert on them. I'm not a good source of information about them. But all of them do have this flaw that they don't reduce the carbon. And the problem is not just temperature change. It's global change. It's ocean acidification. It's what it's doing to our water systems. So it's more than just carbon. So it's true that there may be more reasonable geoengineering ways of reducing the temperature issue.
I really enjoyed how clear your discussion of the modeling and its application, its potential application to policy is in this talk. Have you had a chance to...
Are you enjoying watching it go backwards? You're thinking through the whole talk backwards.
That's very nice as well. But I was wondering if you've had a chance to share this with policymakers, and have they been receptive to trying to kind of actively include more, say, collaborative work with mathematics and that sort of thing?
That's a super question. So I personally have not done a lot of that yet. So we'll talk about me. I'm on sabbatical this year. So the first half of my sabbatical, I have spent really involved in this Math of Planet Earth 2013 thing. It's been wonderful. There's so much more attention being paid to the math behind these challenges. The second half of my sabbatical, I am devoted to finding out how to do that. I'm going to go I'm gradually learning how to meet policy people. I'm going to go to England because it's a smaller country where scientists and policymakers have easier access to each other just because it's smaller. And I really want to do that. I want to make connections between math and policy decisions. But I'm not alone in this. Right now I'm attending a workshop at the Math Biosciences Institute in Columbus, which is a fabulous group of ecologists, mathematicians, economists, and policymakers talking about how we manage our natural resources. And there it's definitely happening that the mathematicians and the decision makers are communicating and talking to each other. But we mathematicians, we scientists have to learn that the stuff that we find super interesting and fun doesn't sound super interesting and fun to somebody who doesn't know our language. It just sounds terrifying, black box, stress-creating, unbelievable, as in unreliable, as in I'm not going to base my decision on this black box that I don't understand. So we have to think about ways to turn the super interesting, deep science and math ideas into sensible rules of thumb, right? We can't expect our managers and decision makers to be scientists as well. Nobody has time to be everything. We want them to be good at understanding the big human institution inside which they've got to make the decision. So we want them to be good at that. So there's a real, this discussion, the conversation that's got to happen between scientists and policymakers, I think, has got to be one based on real respect for each other and finding a language for each other. And the scientist part of it, and not only the scientists, but those of you guys who like science but don't want to be scientists, you don't want to be stuck in a lab your whole lives, you really might like communicating. We desperately need the people who can help us translate the science into rules of thumb, right? So that's another place where your passion might be sort of science without wanting to be a scientist. Boy, do we need you guys.
As you were showing the graph from the very beginning, like the temperature of the world, the globe is rapidly increasing. So are we already at the tipping point?
Oh, that's a question lots of people are asking. So there is not, I think it's safe to say there is not one tipping point for the planet. I mean, I just showed one when we jump down to Snowball and we jump out. But in terms of humans and all the other species living on the planet, it's not a single tipping point, it's lots and lots of little tipping points. It's, does your grazing land become a desert because either you're grazing it just a little too much or because it's got just a little bit drier? Does your glacier melt and therefore your whole community doesn't have water anymore? So it's all these one tipping point at a time, right? And so are we past some of those tipping points? Probably. But are we past all of them? Definitely not. And if we do pass one or two of them, it doesn't, I mean, that's sad, but it doesn't have to mean devastation for the whole planet, right? It can be things we can learn from, things we can learn how to avoid in all the other places where that tip could potentially happen.
So you said that interdisciplinary ways are what you're going to do to like fight climate change, but a previous speaker talked about how when they all got together, or when different scientists get together, they have to like dumb down things in order for like them other scientists to understand and stuff. So how do you plan to like go about it in the way that you're planning to do, but not have it dumbed down?
So yeah, that's interesting. I think that's part of what's so important when I say we need courage, all of us at the level of students and educators. We need courage to learn enough of each other's language that we don't feel that we're dumbing things down. So there, for example, you could have a really difficult theorem in math with a really difficult kind of proof and a whole bunch of technical math behind it that you couldn't possibly explain to a non-mathematician. But the statement of what that theorem is telling you, like there is a tipping point, the graph that's associated with that piece of mathematics is not a dumbing down of the piece of mathematics. Stating it accurately with a graph is not the same thing as dumbing it down. So if you, the scientist, let's say you're the scientist and I'm the mathematician, if you've learned enough math from the kind of conversation we've had today, this very two-way conversation we had, to appreciate what that graph is telling you, then you don't need to know the technical math in order to understand the deep idea, right? So I think it's about courage and patience to learn enough of each other's language to be able to appreciate the depth of each other's subjects and trust each other, right? Interdisciplinary teamwork is about trusting each other to do our hard part well and communicate it to each other accurately. So the dumbing down thing, I think, is about people who have not learned interdisciplinary work. That's part of interdisciplinarity. And one of the difficulties of it is it takes time. Time that if you were not trying to be interdisciplinary, you would be focusing, building your own career, doing whatever you're doing within your little subject, right? So as a society, we are gradually learning to respect and reward the time it takes to learn to speak to each other and learn each other's language.
Are there any other questions for Professor Zeeman? Then join me in thanking her once again.
Thank you, guys. If you're the kind of person that would rather ask your question in private, feel free.